it's really comfortable, just you and me. So just let's do it like a private lesson, okay?
Okay.
I think it will be more comfortable. Okay, you're talking the lecture on microcanonical ensemble, right?
Yeah.
Okay, so we'll do quick recap on this ensemble and then two example questions. Okay, so the characters of microcanonical ensemble. So the first one is to assume that the energy has some constant energy. The system has some constant energy. Some E. Okay, and everything we do in the system is under the assumption that we have some constant energy for the system, and this energy doesn't change. Under this assumption, we're saying, okay, so if the system has energy E, we have a number of states that the system can be in with energy E. Okay, we have states with energy that is not E, and we don't count this state. We want let's do it number of states with energy E. We denote it as omega E, the number of states. And then we have the constant energy E, and we have the number of states, and we're saying, okay, in the microcanonical ensemble, we are assuming that each state we're counting has the same probability for the system to be in. So probability to state I with energy E equals to 1 over number of states. Hey. Shefa. Okay. What we need more? Okay, so under those assumptions, we can calculate thermodynamic sizes of the system. Okay, so we can say that the entropy will be equal to KB, one of the number of states. Okay. So this is when we can count the states of the system, when we have discrete system, discrete states. But what if we has a continuous system? So we cannot count the number of states in this system because we have infinity states. Okay, so what we do, we're taking omega of E, instead of being the number of states, to be the density of states. And we calculate this by taking phi, that is defined to be total number of states up to energy E. Okay, so we're counting all the states from the lowest energy up to the energy of the system. And then we're saying, okay, the density of states only in energy E is the derivative of the total number of states relative to the energy. And then the entropy is given by KB ln of number of states divided by some constant h in the power of d divided by 2, where d is the number of dimensions. Okay, so this is for discrete system, this is for continuous system. Okay, and let's insert here some note that we need to pay attention in continuous system to the particles. We need to see if they're if they are identical particles. Okay, so in discrete system, if we have identical particles, we will just get less number of states. Okay, because we're counting different states. So if we're in discrete system, we just count less. But if we're in continuous system, we need to insert it manually to the entropy. And then the entropy is given by KB, ln of the density of states divided by the constant h in the power of d over 2, and divided by n factorial, the number of particles factorial. Okay, so this is the background where we need for the microcanonical ensemble, and now we can talk in examples. So we'll do one example for continuous system and one example for discrete system. Okay, so what we want to do here, we want to find the entropy of an ideal gas. We want it classical and monoatomic. With n particles. Fixed energy E. dimensional box with volume V. Okay. So because it's tutorial on microcanonical ensemble, so we know we need to use microcanonical ensemble, but let's mark the part of the question that tells us we can use the microcanonical ensemble. Okay, so we have here fixed energy E. Okay, so this is the condition for microcanonical ensemble. We need fixed energy E, and then we're doing the assumption about the probability of each state. But this is the first condition to use the microcanonical ensemble. So we have this condition, we can use the microcanonical ensemble. Okay, and now we want to find the entropy in the microcanonical ensemble. So the entropy is, and we're working in ideal gas, so this is a continuous system. Okay, so the entropy is given so we have KB, ln of the density of states divided by this constant H in the power of number of dimensions divided by 2. And again, we're working in ideal gas, so we have n identical particles. So we need to divide here by n factorial as well. So this is our entropy. So what we need to do is to find the density of states of the system. Okay, so in continuous system, that means that first we need to find the total number of states up to energy E. And how we do it? Okay, so first we need to define our energy, how the energy of the system is defined. So we know that in ideal gas, the energy of the system, let's write it not as E because E is the constant energy, let's write it as epsilon. Okay, the energy of the system is defined by the sum on each particle, and we have energy of free particle. Okay, so we have P squared divided by 2m, and we are summing on all the particles, from the first particle to the nth particle. Okay? Good. So this is the total energy of the system. Now, how we count the states up to energy E? So in continuous system, we're saying such a thing. Okay, so we want to sum on all the states that have energy epsilon that is smaller than energy E. Okay, this is the sum we want to do, and we're summing on the general system. Okay, so summing on all the P's and all the X's. Okay, we're summing on all the states of the system, and our limit is this condition. Okay, so let's see what this condition gives us. Okay, so the total energy Okay, let's do it. Let's do such a thing. Okay, since the particles not depend one on each other, okay, we can divide the integral to the different particles. Okay, the condition is we can divide the different terms of energy for each particle, and the integral we can divide the different terms for each particle. Okay, so we have integral on this condition of d-dimensional P and d and x's. Okay, so for each particle we have d terms of P and d terms of x's. Okay, in total we have dn p's and dn x's. Okay, for each particle we have d p's and d x's. Okay, so this is our total integral. Now the condition is only on the momentum. Okay, we don't have condition on the place of the particle. We can write this condition as p squared is smaller than 2m e. Okay, so we don't have any condition, any limits on the x's. So on the x's we just counting all the space. Okay, and what is integral in all the space on x? So it gives us the volume of the system. Okay, it's like that.
So the integrate is total number of the states
Up to energy.
up to energy.
Because the energy here depends only on p's, okay, we can sum on x's in all the space. Okay, so we have this condition, so we have only states up to energy E, but this is valid only for p's, only for the sum of p's. It doesn't have influence on the sum on x. Okay, so we actually have some integral if we take a three-dimensional system. So we have d in the third x on all the space. So we just have the volume of the system. Okay, so our system is d-dimensional system, right? So we will have let's say if we have for one particle this integral for one particle in the dimensions, we will get the volume of the box, and for n particles we will get the volume of the box in power of n. Okay, so this is the given integral we need to solve, right? This we understand. physically, and then we're just doing math things to solve this integral. Okay?
Can you explain physically the first integral?
Yeah, so we're counting all the possible states, right? All the possible p's, all the possible x's.
So,
But we count only the states that has energy less than E. Okay, only in these limits.
so you see the total energy is E. So why is we count the smaller than E? Not only the energy equals to E.
Here, epsilon.
Uh,
So epsilon E is the given energy the system is in. Okay, the system has energy E, known energy E, and epsilon describe the possible energies the system can have depending on p's. Okay, so E is just a constant, a given constant.
So the energy consists the E, the velocity energy and the volume energy.
Yes, so this is the calculated energy, this is the given energy. And we want the calculated energy to be for the total number of states up to energy E. Okay, we want all the states from the lowest energy up to E energy. Okay, so we want the calculated energy will be smaller than the given energy. To count only those states. It's like we have a space. Okay, so and each dot in the space, each location describe different possible state of the system. Okay, and we can say that this spot describes the system in P1 equals something specific and X1 equals something specific. Okay, and we have this for each dot, and then we're saying, okay, we have some shape, okay, that in this area we're getting that the total energy of the state is less than E. Okay, and outside this area, the total state of the system is bigger than E. And we're summing on this area. We're summing all the dots in this area. Okay, this is the meaning of the integral. So if we hadn't have this condition, we were just summing up on all this space.
Okay. Oh, I know. I understand. Yeah. Good.
Okay, great. So this is fine.
Yeah.
Okay. So we're continuing.
איזה אינטגרל צריך לעשות על זה כדי להגיע למספר המצבים?
על מה? On what?
צפיפות המצבים, את צריכה איזה אינטגרל?
On the density of states.
Yes.
So this is the total number of states, and then density of states is defined by the derivative of this relative to E. Okay, and then you just get the surface of this shape.
And you can do that right now.
Yes, I can do it, but I have dependence on E in the limit, so it's not straightforward. Okay. So in this interval, if we're writing the volume instead of this the integration on x, so we have v in the power of n, and we have integral on the p's under the condition that P is smaller than square root of 2m. Okay, so again, we need to sum on all the space under these limits, and this limit gives us like a sphere, a ball in d dimensions, in dn dimensions. Okay, we have this radius. This will be the radius of the ball. Okay, so we can again look at it in 2 dimensions and say, let's say we have only 2 P's. This will be P1 and P2, and we want to sum. Let's do it with squared. Okay, and we want to sum on all the p's that are smaller than 2me. Okay, so this is a circle shape. Okay, if this is the center, so we want to sum on all those states. Okay, and we have a circle. So here we have the n dimensions and not only 2. So we have a ball in the n dimensions. Okay. Fine?
Yeah, fine.
Okay. Okay, so the formula for general volume of a ball in some dimension d with radius r equals to squared pi r power of d divided by d over 2 gamma of d over 2.
זה סתם יושבים כאן.
לא, אנחנו בשיעור. Okay, so our dimensions d is dn, right, according to the integral, and our radius is square root of 2me. So the total number of states will be equal to Vn from the integral on x, and then the volume of the ball. So we have 2 pi me in the power of dn divided by 2 divided by dn over 2 gamma dn over 2. Okay, and then the number of states is derivative of phi according to b. So it will be equal to Vn 2 pi m in the power of dn divided by 2 e dn divided by 2 minus 1. All of this divided by dn over 2 gamma dn over 2.
Where did that formula come from?
Wikipedia. Known formula. Okay, and then we can calculate the entropy. And we're doing the next assumption. So we're talking on ideal gas. Okay, so we're assuming that the number of particles is big. And then we can go to this density of states and say, okay, since n is very big number, we can neglect this minus 1. Okay. And then the entropy. S equal KB, 1 of density of state divided by H n factorial. So we will get that this equals to KB times okay, so we have n ln v 2 pi m in the power of d over 2 divided by hd. And we have minus ln of gamma function Vn over 2 minus ln n factorial. I miss here divided by 2. Right? Okay. Great. Now we want to write this in a shorter way. Okay, so we're using Stern approximation. Okay, because we're assuming that n is big number. Okay, we can use Stern approximation that says that ln of n factorial when n is big number approximately equals to n ln n minus
עד עכשיו זה טרמו, כן?
כן. Okay, and more than that, we can write the gamma function as a factorial function as well. Okay, so this is Bn divided by 2 factorial plus 1.
Plus?
Right? Plus or minus?
I think minus.
Minus 1? Okay, minus 1. Factorial. Okay, and then we can use Stern approximation on this thing as well. And its total, we will get that S is approximately nkv ln of v over n for m IE divided by dNH in the power of d over 2 plus d plus 2 divided by 2. Okay, after all the algebra. Okay, but this actually doesn't tell us nothing, so we want to derive from the entropy to some other thermodynamic sizes of the system. So we can derive to the pressure, to P, and we know that P equals to T times derivative of S relative to V with constant energy. Okay, and if we take S and put in this equation, do this derivative. Okay, so we are do the derivative relative to V. Yeah, all this is in the one function, and we get that this equals to T nkb divided by V. Okay, and then we're getting the known equation for ideal gas, PV equals to N kBT. Okay, so we succeed to get the equation of state of ideal gas from the microcanonical ensemble.
That was the point?
To see that it works. Yes. Give good.
But it wasn't the question.
We just wanted to find the entropy,
Yes,
but
yes.
then we can
Sneak
see
it
that.
in.
Yeah. Okay, let's see now for discrete system. So in discrete system, it's actually really similar. From the part, we know the number of states. Okay, so we will do a section of finding the number of states in discrete system. Discrete, maybe, I don't know, system. Okay, so we have n particles. In oscillator. With discrete energy levels. Epsilon n equals to an epsilon where n equals 0, 1, and so on. The total energy is E equals to some Q, okay, some whole number Q of n times epsilon. So we have Q quantas of epsilon. And we want to find under this energy, okay, so we again have constant energy, so we can use the microcanonical ensemble. And we want to find the number of possible states we can insert n particles into the system and get total energy of E. So we want to find the number of states. Okay, so in discrete system, it's usually combinatorics. Okay, what does this mean? So we have, let's say we have Q quantas of energies. Okay, so let's describe each one as a ball. Okay, and we have Q balls like this. Okay, now we want to divide these Q balls into n particles. Okay, we can have that one particles have 3 energy quantas. Okay, so it will be in n equals 3. Okay, and we want to divide these Q energy quantas into n particles. So we need to put in this line n minus 1 dividers. Okay, so in total we will get n cells. Okay, we have 1, 2, 3. We can have cells with 0 energy, 0 balls, yeah, with 0 energy, where n equals 0. So we want to insert n minus 1 dividers into this line. And we want to know how many possible ways we can do this. Okay, so this problem is actually a known problem in combinatorics, and its solution is given by, okay, so you can think of it as we have n minus 1 dividers that we want to put in different q plus 1 positions, yeah, 1, 2, 3, 4, 5, 6, 7, 8, and we can put dividers in the same position. Okay, so it's combinatorics with no meaning to the order and with repetition. Okay, so this is given by plus 1 plus n minus 1 on n minus 1. So, okay, by this binom, we want to choose n minus 1 places, okay, from q plus 1 places, okay, with repetition and no meaning for the order. Okay, so this is equals to q plus n minus 1 factorial divided by n minus 1 factorial q factorial. Okay, so this is the way to do to calculate discrete systems. Okay, we need to use combinatorics, and from here it's the same as we did in the continuous system. Okay, we're calculating the entropy, and then we can derive two different thermodynamic sizes in the system.
What was the logic? You wanted to...
You want, let's do it in an example.
Did you
in small
want the
system.
total energy to be
So the total
combination of energy levels?
Yes, so the total energy is Q, some whole Q times epsilon. Okay, so this is represented by Q balls. Each one has epsilon energy. And then you're creating cells that in each cell you have some number of balls that represent the total energy of the particle.
And the cells are different ends.
What?
Small n.
Yeah, so if Q was equal to 5, okay, and we need to divide it by 3 particles. Okay, so we can have that one particle has all the energy and the other two has 0 energy. Okay, we can divide it.
So 2 particles can have the same energy.
Yes. Yes, it's 5, so no, but yes. We can put the divider here, so we have 1 and 4. Okay, so we can put our dividers in each place between the balls, and each cell tells us how much energy we have for one particle. Okay?
Yes.
Okay. questions? Okay, so this week we won't have exercise. Okay, next week we will have exercise on this tutorial and the next tutorial.
What do you mean?
אין תרגיל בית השבוע, שבוע הבא יהיה תרגיל בית משולב על שני התרגולים. כן. אוקיי.
Thank you.
Welcome.
חשבתי אין תרגול.
לא לקחת את הקורס בקיץ?
לא.
נכון, עשית את זה לכיף.
כן,